Hello and welcome to Equity Education, the chemistry version. Okay, so today we're going to be looking at moles and basic calculations. Okay, so if you'd like to open your booklets, we'll get started. Right, okay, so what do we mean by atoms and molecules? We'll start with that. So, simple definition for atoms is the smallest particle of an atom that can exist. There are lots of definitions of atoms, but we'll just stick with this one for now. And moving on to a molecule. So what is a molecule? It's a particle made up of two or more atoms that are chemically bonding together. This word chemically is important. We need to include this when we're talking about the definition of a molecule. And also, the number of atoms in a molecule is fixed. So we can't change the amount, e.g. So let's have a look, see if you can think of a molecule. One of the obvious ones, obviously, is H2O, water. So this is an example of a molecule because it's chemically bonded together. The oxygen atoms and the hydrogen atoms are chemically bonded together through covalent bonds, and we have a fixed number of atoms within this molecule. So we have two hydrogen atoms and one oxygen atom. If I were to, for example, do this, H2O2, I have changed the actual molecule. This is now not water because it doesn't have the same ratio of hydrogens to oxygens. And just as a side, this would be hydrogen peroxide. Okay. Right, so moving on. Balancing equations and molar ratios. Let's have a look at this chemical equation below. So we have 2 sodium hydroxide plus H2SO4, which is sulfuric acid, forms sodium sulfate and 2H2O. Okay, so we've got some numbers here. We have some big numbers and we have some small numbers. So what do the small numbers in each substance tell us? What do you think they are? Okay, so the small numbers in each substance tell us the number of atoms in the actual molecule or compound. I'm going to write molecule or compound. There is a slight difference, but I might interchange between them. We don't need to worry too much about that at the minute. Okay, so for example here, so we said the number of atoms in the actual molecule or compound. We'll take sulfuric acid, for example. So this tells me that the small numbers here means that I have 2 hydrogens, 1 sulfur, and 4 oxygens. So the number to the right of the element tells us how many of that atom is actually in the molecule. Okay, so moving on. What do the big numbers before each substance tell us? Well, they tell us technically the molar ratio of the compounds in the reaction. And I will write as well the amount needed for each substance to react with each other in the reaction. So technically we're talking about the molar ratio, but just for clarification, we'll also write the amount needed for each substance to react with each other in the reaction. That will become a bit more obvious as we go on. Okay, so if we go back to this equation up here, we can see that we have these big numbers in front of the molecule or the compound. So this tells me, according to this definition here, the molar ratio, that I need 2 moles of sodium hydroxide to react with 1 mole of sulfuric acid to form 1 mole of sodium sulfate and 2 moles of water. Okay? Now, if there isn't a number such as here before sulfuric acid, a big number that is, that means that it is equal to 1. Okay? And quick tip, so you need to make sure that the number of atoms on the reactant side adds up to the number of atoms on the product side. This is important when you're balancing equations. So if we take the example above, so I'm going to write it again. So 2 moles of sodium hydroxide plus 1 mole of H2SO4 forms 1 mole of sodium sulfate plus 2 moles of water. We can check to make sure that the number of atoms on the reactant side adds up to the number of atoms on the product side. So here, when we see this big number in front of sodium hydroxide, that means that really we have 2 sodium hydroxides and we have 1 H2SO4. This side we have 1 mole of sodium sulfate, so I can just write this, and we have 2 moles of H2O water, so we have 2 H2O. Now we can have a go at adding these up. So how many atoms do I have on my reactant side of sodium? 1, 2. I have 2. How many oxygens? 1, 2, 3, 4, 5, 6. So oxygen equals 6. And lastly, how many hydrogens? 1, 2, 3, 4. So we have 2 atoms of sodium, 6 atoms of oxygen, and 4 atoms of hydrogen. Let's have a look at the product side, see if it correlates, if it equals. So here, how many moles of sodium do I have? I have 2. How many moles of oxygen do I have? I have 4 here, 5, 6. How many atoms, excuse me, I keep saying moles, how many atoms of hydrogen do I have? I have 4. So we can see that they add up. And as you just probably noticed, I've also missed on this side that we have 1 sulfur, and on this side we also have 1 sulfur. So we can clearly see that the number of atoms on the reactant side is equal to the number of reactants on the product side. And this can be explained by talking about this word stoichiometry. We're not going to go into that much detail about it, but all we can say that the total mass of reactants must equal the total mass of products, which it does in our example. Okay, so that's a quick introduction, and now we're going to go into looking at some calculations, some basic calculations. Now the first section, I'm going to talk about Avogadro's constant. Now these calculations are slightly more difficult than the next calculation, so if you want to skip this section because you're unsure and come back to it, that's perfectly okay. Okay, so let's talk about the mole. So the mole is a way of measuring amount of substance that does not require very large numbers, which is important. And we can say that 1 mole is equal to the value of 6.02 times 10 to the 23, which obviously is a massive number. This is known as Avogadro's constant. So we can say that 1 mole of anything is equal to 6.02 times 10 to the 23. So I'm talking about anything. So I could say we have 1 mole of sodium atoms. It would equal 6.02 times 10 to the 23. I could also say how many elephants are in 1 mole of elephants, and it would equal 6.02 times 10 to the 23. Okay, so obviously we've just talked about this. So Oh, not quite. So you have to make sure that you understand the words in questions, okay? And make sure you know these definitions. So have a go at answering these questions. I'll give you a couple of minutes and we'll see how you get on. Okay, so first one. How many atoms are contained in one molecule of Cl2? Now, if I have one molecule of Cl2, it must mean that it looks like this. This is one molecule. I have how many atoms within this? So I have 2 chlorine atoms in one molecule of chlorine. Right. Now this is a different question. So how many molecules are contained in 1 mole of Cl2? Okay, so we know from up here that 1 mole of anything is equal to 6.02 times 10 to the 23. Therefore, 1 mole of chlorine molecules in 1 mole of Cl2 must be equal to 6.02 times 10 to the 23 molecules of chlorine in 1 mole. So you need to make sure that you know the difference between this. So how many atoms are contained in 1 molecule and how many molecules are contained in 1 mole. Okay, we'll do some calculations on this a bit later, but first we're going to do some Avogadro's calculations. Right, so formula that you need to know is number of moles equals number of particles divided by Avogadro's constant. Okay, so this is an important calculation. This is an important formula that you need to remember. We can write it in chemical notation as N equals big N, number of particles, over Na for Avogadro's constant. Again, you may see different chemical notations for number of particles and possibly for Avogadro's constant. Just be careful if you're looking at other websites or other chemistry books what their notations are. So in my examples I'm going to use number of particles as N, and for Avogadro's constant I'm going to use big N A. Okay? Right, so now I've given you this formula, I'd like you to have a go at calculating these questions. Okay, so have a go, let's see how you get on. Okay, so how do we do? So first one, calculate the number of molecules in 0.5 moles of methane. So number of molecules in 0.5 moles of methane. So I always like to write down the formula that I am using to begin with. Now I am trying to calculate my number of molecules, yeah, which is equal to N, my big N, my number of particles. I know Avogadro's constant, I know my number of moles, so I can rearrange this equation to give N equals N times Na. I can then put in my amounts, so 0.5 times by 6.02 times 10 to the 23, which equals 3.01 times 10 to the 23. So I know that I have 3.01 times 10 to the 23 molecules of methane in 0.5 moles. Now I've used this formula, yeah, but I probably could have done it in my head, but it's always best to use the formula because I know that 1 mole of anything contains 6.02 times 10 to the 23. So if I have half that amount, I must have half the amount of Avogadro's constant, which equals 3.01 times 10 to the 23. Okay, moving on. Calculate the number of atoms in the above example. Okay, so I know from the above example that I have 3.01 times 10 to the 23 molecules of CH4. So I know that. However, I now have to calculate the number of atoms in this. We know that atoms and molecules are different. And I know, if I look at this, that one molecule of CH4, methane, contains how many atoms? It contains 1 carbon atom and 4 hydrogen atoms. So it contains 5 atoms. Therefore, to work out my number of atoms in this, I must have 3.01 times by 10 to the 23 times by 5, which gives me a value of 1.51 times 10 to the 23 atoms. Okay, and this is why it's important to make sure you know the difference between these words, atoms, molecules, and moles, yeah? Because otherwise, when you do calculations, if you get confused, you're going to get the wrong answer. Okay, and lastly, right, so this is well, no, it's not the most difficult, it's just a different calculation. So calculate the number of moles in 1.302 times 10 to the 24 atoms of sodium. Okay, so 1.302 times 10 to the 24 atoms of sodium. So I know that I need to use my formula, N equals N over Na. I know my number of atoms. I know Avogadro's constant, 0.02 times 10 to the 23. So I can work out my number of moles, which equals 2.16 mole of sodium. Pretty straightforward. Okay, right, so we're now going to move on to another section. Okay, so we're going to be talking about basic mole calculations. Okay, so now we're going to be looking at basic mole calculations. So using moles, mass, and MR in calculations. And the formula that you need to know to be able to work these out are N equals M over MR. Now we're going to be using mass in this example. There are other units which we can use to calculate N, but these basic calculations we're going to be using mass. So N equals M divided by MR. Now you may have been told to use a triangle to work out how to rearrange the subjective equation. Get rid of that. Just work out how to do it from a mathematical point of view. It will really, really help in the long run, especially as you move further and further into your education, if you can rearrange algebraic equations. It's not particularly difficult, and that's what you're going to have a go at doing now. So please do the following questions and let's see how you get on. Okay, so first question, make mass the subject of the equation. If I want to make M, mass, the subject of the equation, I need to times MR by both sides, which means mass will equal N times MR. Not that difficult, yeah? And if I want to make MR, which we call the molar mass, the subject of the equation, it means I need to, we'll use this example, I need to divide by number of moles here, so MR equals M divided by N. So as long as you remember this equation here, you should always be able to work these out here. So let's move on. So meaning and units. So meaning N, as you properly guessed, is mole, and my units are mole. We take the E off. I don't know why, chemists are apparently lazy. Okay, M stands for mass, and our units are grams, which is G. And M is my molar mass, which has units of grams per mole. You may see this written slightly differently. You may see it written as grams per mole like this. But I'm going to stick to the top one. Yeah. And if you think about it, where these units come from, it does make sense. So if we have N equals M over MR, and we change it to MR equals M over N. If we put these into our units here, we have grams over mole. I need to bring this up, therefore grams to the mole to the -1. So that's where my units for molar mass come from, and it can be explained by looking at our equations that we've just been through. Okay, so calculating the molar mass. So the molar mass can be calculated by adding up the individual atomic masses of each atom in the formula. Where do we find these atomic masses? Well, hopefully you've got your periodic table in front of you, because I'd like you to have a go at calculating these MRs. Okay, so I'll give you a couple of minutes and we'll go through them. Okay, so calculating the MR, the molar mass of the following. So Cl2 means we have 2 chlorine atoms. The AR, the atomic mass of chlorine, is 35.5 by looking on the periodic table. I need to times by 2, so it must equal 71. Sodium chloride. Sodium has a atomic mass of 23 plus 35.5 for 1 chlorine atom equals 58.5. And magnesium hydroxide, right, so magnesium is 24.3, oxygen plus is 16, hydrogen is plus 1, and then we have 2 of them here, so I'm going to times by 2, which equals 58.3. Again, just to go through this, like when we were talking in our previous example about what do the small numbers means, it means the actual number of atoms in a molecule or compound. So here we would have Mg and OH and OH. Yep, so I have 2 of whatever is in the brackets. Okay, so moving on, let's do some calculations. Right, so I've given you the formulas, so what I would like you to do is that I want you to have a go at doing these. If you get a bit stuck, we'll go through them in a minute. This probably should take you, I would guess, between 5 and 10 minutes, but don't rush, take your time and see how you get on, and we'll go through them soon. Okay, hope it went all right. So let's go through them. So answer the following questions. Calculate the amount in moles of 8 grams of FeBr2. Okay, so what's the first thing I need to do? I need to write down the formula that I'm using. So N equals M divided by Mr. So I know my mass, which is 8 grams. I know this is a mass. How do I know this is a mass? I know this is a mass because I can see the units here. Yeah, grams, that's my units for mass, so I know that's a mass. I can calculate my MR by adding up the individual atomic masses for each of the elements in here. So I can do this by adding these up, so we'll go through that. So FeBr2, so Fe is equal to 55.8, and I have bromine, 1 atom of bromine 79.9 times by 2, which gives me a value of 215.6. Right, now I've got my values, I can put them in. So 8 grams is my mass divided by my MR, 215.6, which gives me a value of 3.71 times 10 to the minus 2 moles. Okay, so pretty simple. As long as you can add up or calculate your MR, you should be laughing. You should be able to answer these questions. Moving on, so calculate the mass of 0.25 moles of sodium carbonate. Right, so again, I need to write the formula I'm going to use, N equals M divided by MR. I need to rearrange this equation, so M equals N times MR. I know my number of moles. I can calculate my MR of sodium carbonate. So I have 2 sodiums, I have 3 oxygens, which is 16, and I have 1 carbon, which is 12, which gives me a value of 106. Now I can stick it into this equation. So my number of moles is 0.250 times by my MR, which is 106, which gives me a value of 26.5 something. What do I need to write here? Don't forget, always put your units, so 26.5 grams. Okay, and thirdly, calculate the MR from the following information. 46 grams of sodium contains 2 moles. Right, unsurprisingly, N equals M over MR. I need to rearrange this equation, so MR equals mass over N. I've got all the information I need. Here's my mass because it's grams here. So 46. This tells me that it's moles, the units, divided by 2, which gives me a value of 23. And I'll put the units on. Grams per mole minus 1. Okay, just before we go on, now when we're talking about molar mass and calculating the molar value on the periodic table, it's slightly different, but I'm not going to go into that at the minute. For the time being, all you need to know is that if you need to calculate a molar mass or an MR, all you do is add up the individual ARs of each atom in the molecule or the compound. Okay, so moving on. Okay, so now we have to calculate the number of atoms in 0.05 grams of water. Now if I calculate my number of atoms, that must mean that I must be using this formula. So this is my number of atoms that I need to calculate. However, I don't have a number of moles. In the question I do have a mass, my grams, and I can calculate my MR, which must mean I can calculate my number of moles using this formula. Okay, so that's what we're going to do first. So my mass of water is 0.05. My MR is 18. You should be able to write this down. So MR, we'll do it quickly up here. My MR of water is H2O. So I have 2 plus 16 equals 18. So this will give me my number of moles of water, which 0.05 divided by 18 equals 2.78 times 10 to the minus 3 moles of water. Now I've worked my number of moles out here, I can transfer it to here. Yep. And I need to rearrange this equation to be able to work out my number of, we'll say particles for a certain reason here, my number of particles. So N equals, big N equals my number of moles times by Avogadro's constant. I know my number of moles, 2.78 times 10 to the minus 3. I know Avogadro's constant, so 6.02 times 10 to the 23, which gives me a value of 1.67 times 10 to the 21. Now, are these atoms? Yeah? Well, no, they're not at the minute. These are the number of molecules of water. Yeah? We've worked out the number of molecules of water. Now, the question asks for atoms. Therefore, we have to do something with this number. We know that there are 3 atoms in 1 molecule of water. Therefore, we'll have to go up here. 21 times by 3 equals 5.02 times 10 to the 21 atoms of water. Okay, hope that makes sense. Just as a quick note, we'll write up here that there are 3 atoms in 1 molecule of water, just if you're looking back on your notes, so you know where this number comes from. Okay, right, so that's our answer to a question. If you're a clever clogs, I'll quickly show you that you could have done it a slightly different way. So if you look over here, N equals N divided by Na, N equals M divided by Mr. We know that the number of moles must be the same for each of these equations, so we could have said that N equals Na equals M divided by Mr. Okay, so this is just a different way of doing it. Doesn't matter which way you do it. Therefore, to work out my N here, I could say that N is equal to M over Mr times by Na. I could put my values in, which gives me 0.05 divided by 18 times by 6.02 times 10 to the 23, which gives me 2.78 times 10 to the minus, it doesn't give me 2.78 times 10 to the minus 3. It gives us, what does it give us? It gives us 1.67 times 10 to the 21 molecules. And again, once we've got this value, we'd still have to do this part. Now, that's another way to work it out. Either way you can do it, it's entirely up to you. I think the first way is slightly easier, but you're more than welcome to do it the other way. So, again, I hope this was useful, and I will see you again next time. Okay, bye-bye.